For one of the few people that I've kind of had the pleasure and dared to invite on the Data-Driven Design Day event series several years has been my former colleague and current professor of Aalto University, Antti Oulasvirta. And every year he's brought up something a little bit different, and I'm now very much expecting what he'll say this year. Welcome, Antti.
Thanks. So the name of the session is today Dystopia, Utopia, and Reality. And I'm in the middle, so I'm supposedly given the utopian view. And I was meeting a very interesting practitioner last month in New York. I was giving a summer school there. And there was a guy called Rob Beal, and we were discussing, well, how should we frame our work for designers when we talk about AI? And previous talks have been pretty technical that I give, and he was suggesting that why don't you use the word computational superpower, to talk about AI. And I think it's a good metaphor. And last night, I was thinking that what kind of movie reference could I make to liven it up a little bit. And I was thinking, would it be the Holy Grail of Indiana Jones? Well, we know what happened there. Would it be like the Jedi Force? Well, that has the dark side. What about the Lord of the Rings? Well, that makes people invisible, so probably that's not a good idea. And I came up with this one. Have you seen the Avengers Endgame movie? And do you know what the Infinity Gems are? These are giving you the power to manipulate and penetrate time and soul and space and all that. And you can combine them in unique ways. So I'm going to use this metaphor to get it started. And I'm going to introduce you to 3 superpowers. Number 1, more accurately predicting how your users will react to your design decisions. Number 2, doing 1 million sketches or design ideas per second. Number 3, going beyond data, going beyond the shallow shadow on the wall that is your data, and try to see the causal mechanism, the human that produced the data. With that, I want to say hello from our group. This is our group from last year. We have people who do computational modeling, machine learning, optimization, and also design research. And you're going to see those combinations in different forms. So we don't only do machine learning, and for a good reason that I'm going to talk about. We look at regular interfaces. So we do everything from buttons to keyboards, to graphical interfaces, web UIs, gestural interfaces, and so on. And we want to improve their design and interaction. And we realized quite early, let's say some 4 or 5 years ago, that if you want to bring in AI into this business, as has been said here before, you need to go via the designer. So trying to automate something is just not going to fly. Well, in order to do that, you need to understand a little bit how designers think, how they work, what their practices are. And to that end, I took this taxonomy. I guess most of these are pretty familiar to you. The designers, what they do, they create artifacts, they solve problems, they make sense of very complex things, they reflect. And I brought up this new one from a book that I like, which is by Dorst. It's called Frame Innovation. What designers also do is they come up with completely new frames for thinking about products and interaction. I have not started this field. This field has been in existence since the cybernetics, and more or less every method in AI has been tried and tested and failed in this business of user interface design. Let me give you a small gallery of where we are and what we have learned from that history. August Dvorak, you may know from the Dvorak simplified keyboard. He was not using computational methods, but he was putting out the idea that we should be informed by psychology and behavioral sciences when we take actions like, or decisions like, reorganizing how a keyboard should be used. And he did that manually. So over many years, he reorganized the layout and got pretty good results. So he was saying that, let's bring in psychology. But he didn't have any computational tools. Around 1970s, there was interest from computer science. Computer scientists were looking at problems like the keyboard design problem, and they tried to formulate those problems using methodologies and theories that they know. So for example, the keyboard design problem was formulated as a quadratic assignment problem. And then that happens to be NP hard, and there happens to be very good solutions to that. So computer scientists were sort of happy. Those particular methods that they developed were never used for anything real. They were just showing that, okay, we can do that. They were happy with that. Well, in order to go from that, you need to actually bring in more information about people, and you need to do that in the form of models. You need to codify your assumptions about people in some way, and cognitive models seem to be like the way to go around 1980s. And there was a lot of enthusiasm about it, and those models were actually pretty good, in the order of 15% plus minus prediction error for pretty complex tasks. So pretty good models. However, the models didn't do any design, right? You have to do the design, and then you have to give it to the model, then the model can evaluate it, right? And there was no way of matching or fitting those models to data, right? So you do the model, and then you don't know, well, how do you represent a particular person, for example, with that model? So people wanted to still use optimization, but they needed to get rid of cognitive models, and what they did, they started encoding in a rule-based system designers' heuristics and knowledge. And it quickly grew out of hand. So these systems started to be over-engineered for a particular problem, very complex to manage. Now you probably wonder who's going to be here, and that's more or less everybody since 2014 when the deep learning made a big breakthrough. Everybody thought that I'm going to take Keras, I'm going to take PyTorch, and just crank the shit out of it, right? Well, it wasn't that easy, right? And this is one of the areas where we don't see similar breakthroughs, user interfaces, as we see in speech, image processing, computer vision, and so on. And there's a reason for that. I'm going to come back to that later. But we can actually learn quite a lot from all of these, and we have advanced in parallel in some of the methods that we have coming from computer science, especially modeling and optimization and machine learning. And in our group, we develop a combination of those powers for what we call a new type of intelligence for design. So if you take a regular, let's say, machine learning approach, you have a design, you have some data, you put it to some black box, you get something out, prediction or classification or something like that. We don't want to do it like that. We want to bring in behavioral sciences because we believe that in order to design, you need to understand your user. You need to understand the human factor and take that as a first-class object in your work. And that means that you have to codify assumptions about people in a way that you can control, you can validate, and so on. So what does it mean? We'd like to generate and enhance interfaces with and for designers. In order to use computation therein, we need to formulate their decision problems as computational problems. In order to bring in behavioral sciences and that knowledge, we need to use models, and they are at the intersection. They have to bridge between the design, the algorithm, and the human model. And of course, computation can furthermore help us learn those models from data, right? Okay, going back to the infinity games, let me concretize these superpowers that I want to talk about. So let's take a very mundane-looking design example. Let's say that you're designing a menu, and this is an example that we've been working on quite a lot. Let's say that you're designing a menu, you have to make lots of different choices. You have to decide whether you're going to do a menu, what are the functionalities, how do you label those functionalities, what kind of interface widgets you're going to use, how you're going to order them, how you're going to group them, what kind of shortcuts you're going to give, and so on. And there are three recurring problems in interface design problems like this. Number one, when you take an action, you put the save over here or over here, you need to have some sort of anticipation. Well, what's going to be the consequence on your user? That's hard. Number two, you need to combine multiple design decisions to come up with a particular full design, right? And those things are quite fragile. You take the save from here somewhere else, and people will not find it anymore, any longer because they only see save as, right? And finally, of course, you need to design this for people, right? You need to touch data. And you need to go beyond the data to say that this is what people need, this is their capabilities, this is how they learn. So pretty deep psychological factors you need to take from that data. And we'd like to augment the cognition of designers, especially coming from two weaknesses in respect to these three problems. I don't know if you saw a couple of weeks ago, there was a result from my colleague at Aalto University, Katja Hölte-Otto. she's been studying what she calls empathic accuracy of designers and showing that even in very favorable conditions, the accuracy of you understanding a person is pretty low, right? So the hit rate in empathy is very low, so we should not rely on that. So that's number one. And of course, it's understandable because designers are rarely psychologists. They only can use their own intuition and kitchen psychology to do that. Second, as we have heard today, people are biased. They're also very limited in this kind of planning and reasoning type of task, as we know, for example, from chess. Now, there are some people in the audience who want to know what we really do behind the curtain. And I took this diagram that we used internally. And one of the points here being that it's not just about deep learning. We actually have to combine other capabilities as well in pretty complex systems. So let's say that this is the user land. The user lives here. User produces some data. We need to infer something about the person, and that we do with probabilistic inference. The reason is that then we can be sure that we don't overclaim, overinterpret that data, because it's always very scanty about the particular user. Once we have that, we have parameterized our predictive model, which we can use then to make predictions about that interaction, which we can then give to the combinatorial optimization as a so-called objective function. Now it can ask when it speculates about, what would happen if I placed the item here? What would happen if the color was red? And so on, with the help of this model. Of course, these models can come from theory. They can come from data. We can use deep learning models. We can use Bayesian models. We can use theoretical models, whatever makes it. And of course, we need to make the whole loop somehow controllable for the designers. And we can actually use machine learning again here in order to adapt this loop to the wishes and ideas of the designer. I'm going to show examples here as well. One way you can think about it is that we don't directly go to deep learning, which would be this end of the spectrum. So let's call this end of the spectrum Blackbox Modeling. You crank some data to a model and you try to get some predictions, classifications out. Well, what's cool about deep learning is that it has very high representational power, but on the other hand, it's very data hungry. So suddenly, if you have data from a couple of designs, you have lots of data from a couple of designs, and you want to leap from those designs to some other design, it becomes a problem. This is one issue with deep learning. Whereas if you go the other way around, you say that I'm going to start from theory, I'm going to start from models, they are fully controllable, you understand how they work, but they're very hard to construct, right? Years and years of work to build a good model. So we'd like to be somewhere in between of this over-engineering and under-engineering, right? And we can call that gray box modeling. This is a term that they use in engineering. And what does it mean? For example, let me give you two examples. So let's say that you have a fully white box model of a human cognition, and you have some data. Well, you can use machine learning to fit the parameters of the data, of the model to that data. That's one way of using it. If you go to this end of gray box scale, then what you get, for example, you can use something like in robotics, where they train a deep learning model offline in a simulated environment with the human model, right? And then you put it back to the real world. It's going to be much wiser acting like that. Okay, with that, a little bit of a methodology of how we do things. Let me show you the superpowers one by one. So number one is prediction, and this is, of course, something that started around 1960s already with information theorists applying information theory to human motor capacity and so on. And there's tremendous progress ever since. We now use machine learning, especially reinforcement learning, deep learning, Bayesian optimization, when modeling the user. And I want to show a little bit of that progress. So before that, I want to show some properties of a model that you need in order to design with the model if you're an algorithm. So if you're an algorithm, let's say that we have some very, very simple model, just for sake of illustration, it doesn't matter, but let's say that it has some variables. It has some structures and variables. And those structures and variables, let's just call them parameters. They're anything that we can change from the outside. They have to touch the design somehow, right? We have to be able to change the design that is going on inside of here. We also have to express differences between people and contexts. So these are the two qualities that we necessarily need for computational interaction. Also need to get some prediction out that we can then verify and act on in the algorithm. What's nice about these kind of models, because as you see, you can actually solve it for any other variable there, is that you can go the other way around as well. You can ask, for example, if I want this kind of interaction, what should the design be? Or what should the user be like? Well, the models are actually way more complex. There was a lot of work on mathematical model, and now there's work again on probabilistic models. More recently, and these are actually very nice because you can plug them easily into an optimizer and then run it. Recently, there's a lot of work in applying deep learning as a model of human mind, especially human vision, and there are big breakthroughs in terms of, for example, saliency modeling. These are actual results from our lab. Here's an interface that the deep learning model has never seen. Okay, it has been trained. It's a theoretical model that has been trained on other examples. And then this is real user data on where user would look at first. And this is a prediction that comes out of the model. So we have pretty good predictive accuracy in terms of saying where would the user look at first. So this is one example of deep learning coming in use in prediction. The second one I want to show, this is way more esoteric, but we're very interested in very low-level interaction like buttons and trying to optimize buttons for different purposes. And one of the first things that we needed to have is a model. And we built a robotic model of the human finger and the human key pressing cognition. And there was a key ingredient, Bayesian optimization, which model how people learn to press a button. So you can give this robotic finger that has human-like capabilities any button, and it tries to learn it. Learn to press it. In like 10 presses, it gives a little bit human-like presses out as predictions. You can look at the velocities and forces involved, and they tend to be human-like. What's nice about it is that it has this capability of self-organization, so it can learn if you change the goal, if you change the button design, if you even change the anatomy of the robot, it figures out a way to press the button. We have other examples using the same principle, for example, for visual search tasks on graphical interfaces. And what we do in our group and with our colleagues, we've been doing this for over a year now. We work with other colleagues and we try to get models and metrics into one place. So this is a service you can access that. It's interfacemetrics.aalto.fi. You can put in your URL or screenshot. You can select metrics and models. It's not comprehensive, but there's 20 plus different things you can try out. You can get then a dashboard sort of comparing your design and giving all these metrics for the particular design that you put there. What's nice, this is completely free. You can go and download the full repository. Superpower number 2, optimization. I want to talk about how optimization can help you solve really, really hard problems in design and how it can help you explore new ideas, especially trying to get you out of that fixation state and get you roll on and sort of explore the space more broadly. And this is the point where I want to bring up deep learning, because also in our group, we've been trying to use deep learning for combinatorial problems. And every time we do that, we see that it's quite feeble for that. It's very good for other purposes. When you try to organize layouts, you're limited to quite few elements at a time. And the reason is inherently that it's a stochastic gradient-based methods, and these problems are inherently something else. They are combinatorial by nature. I'm going to show on the next slide. And this, what happens is that when you start doing deep learning in this area, then you end up with very involved models and that are very difficult to construct and also very difficult to engineer and change. So, in the area of UI generation, I'm not talking about graphic design, for example, then there's limited success. So how you want to do that, you want to represent your problem so that it's inherently taking into account the type of problem that you're dealing with. Or the properties of that. So for example, what you see here is a branching tree that represents a keyboard layout problem. So every branch is a decision, and what's happening inside of the optimizer is that it sort of splits the design space into a tree, and it peeks into these branches and it asks, well, how good designs can there be in this branch? And it uses mathematics then to see that, okay, there's no good design in this branch, and it cuts the branch off, and you don't have to look at it ever again. So this is behind the power of some of the optimization methods. We use this kind of principle for redesigning the French keyboard layout standard, especially we worked with the French government standardization organization for three years, and this came out this April. There's a special character redesign for this keyboard, and now the first manufactured keyboards are coming out. And we formulated a design problem that had 4 objectives: learnability, familiarity, ergonomics, and performance. And then we gave a method like that I just showed these problems many times in iteration with the committee, and we got this the final result. I mean, what's interesting about it is that this final problem was immense, 10 to the power 200 possible designs, so completely out of reach of human problem-solving capabilities. So what's nice, if you take this superpower number 1 models and you put them into these optimizers, you start getting interesting things. For example, you can take human visual system models and you can ask, well, how would you show very complex piece of data? And you ask the optimizer to consult those human visual system models to select, for example, what the opacity should be or what the size of the marker could be, so that you get more structure out for the human eye. If you have something more involved, let's go back to the menu case. If you have a very good model of human navigation in the menu, you can use that as the objective function. And these are actually computer-generated designs. This is one for Reader. This is one for Firefox. All you need to do is you need to give a list of commands, frequencies of commands or importances of commands, as well as pairwise associations between the commands. And this is what comes out. So we use a model called the information foraging model as the objective function, and just crank it out of the integer programming optimizer. These are actually faster to use than the commercial designs. We compared in an eye tracking study how quickly people can find items. Okay, so we work a lot on formulating interface design problems, like how would you lay out things, how would you support multitasking, how would you schedule things, and we formulate them as known computer science problems, like assignment problems, selection problems, packing problems, and so on, so that we can identify the most suitable methods and understand the complexity of those problems. Now, what's cool for designers is that then you can actually make new kinds of tools. So this is a tool that auto-completes layout. So what you see here is a canvas. And this space is workspace, just like in Microsoft PowerPoint, for example. So whatever you put here, the optimizer treats as fair game for that to propose how you want to place on the canvas. So you can be lazy. You can say that I want the heading to be here. I don't care about the rest of the elements. They just need to be there somewhere. I'm going to put a few elements here. And then the optimizer is computing in the background what are called diverse solutions to the same. We can systematically span the space of alternative designs to this problem. Then you can pick one and start editing from that. And just last week, we completed the first empirical study of this. We had 16 professional designers doing design or wireframing tasks with this, and nearly half of their designs consisted some suggestion by the optimizer. It's a good success rate, given that they are not novices but real designers. Final superpower is that of inference, and we've been discussing about machine learning, and normally it's about classifying people or predicting next actions or whatever. But you can go beyond that. You can actually have causal explanations and causal predictions for people's action. So what does it mean? Let's take any of those simulators that I showed. They are complex simulation models you can run against any design, but you need to fit it to your particular user segment or particular user population. And this is one way of illustrating what we do. So let's say that this box is all the possible behaviors of a person in your system. And your user has produced one particular dot there. And you want a simulator that comes as close as possible to that user, reproducing the data of the user. And once that happens, the internal parameters of that simulator are a good approximation of the real user's parameters. So you can use what is called Approximate Bayesian computation for this goal. So it allows us to do some pretty amazing stuff. Right? We can take just clicks and click times on a web page or menu. And we can fit a generative model of menu behavior to that data and go way beyond that data. We can, for example, this is an example that we try to estimate some pretty intrinsic properties of the visual system of the user. Saccade duration or fixation duration. And then once we fit that model, we can then regenerate user data. And we can change the design. So we can have a new menu that the user has never seen and ask, well, how would the user behave here? We had a pilot project with Elisa where we applied something like this for corporate site. We look at clickstream data and want to see where do people get lost. So we fit navigation models to that corporate site. And we can say that, okay, this part of the corporate site structure, your users are getting lost. there's a lot of possibilities that we're not yet tapping into. You can take any model that then has these properties that I told, and fit it to your clickstream model, clickstream data. And if you use probabilistic inference, you're not going to be over-interpreting your model. You can also feed it to designers. For example, we recently did a system that has been trained on Pinterest mood boards, and it can do a mood board on its own, but it can also fit the style of recommendation that it does here to your style and to your problem at hand, and make one suggestion at a time, trying to help you construct a nice mood board. Again, we work a lot with professional designers. They preferred, 14 out of 16 said that they'd like to use something like this. Now, Lassi is getting anxious, and I want to give you a final, very positive message of uniting the superpowers. And one metaphor, if you allow me to bring one more, would be that you have something like the self-driving or semi-self-driving cars. So as a designer, you can set the objectives of a self-organizing, self-optimizing web page, and you can kick it off. So this is something that you can see downstairs with Markku and I, who are there next to the entrance. So looking back, we're still working hard to support reflective practice, frame innovation. It could be that they're never going to be supported because they involve some deeply linguistic, social, cultural, bodied things. But we can support things that are close to something like chess is, like problem solving and finding alternatives. And there's quite a lot of scope that you can do with the modern methods in that space. And as you saw, we can go further with Bayesian methods when we try to make sense of data. So also help designers to be better. Lassi, last slide. I wanted to go back to the Lord of the Rings. You get invisibility, but you lose something. And similarly, over our studies, and this is touching on the dystopian part of the session, we've seen things like people reporting that they lose control, they start to over-rely on automation, which means that they are afraid that they are going to lose their skills. And I think this is the most worrying thing, that when you get the artifact out, the ultimate particular artifact, you don't feel like it's yours. You feel like challenged by the system who did something like that. I believe that there will be space for optimizing interfaces as a service, supporting designers, sketching and wireframing with these kind of methods that will be integrated into design tools, and our group works on that topics. We are working hard to, in a new project that is hopefully funded by Business Finland, to use these human simulators to go to the next step in data analytics. And one of my career goals is to help anybody with any kind of capabilities or disabilities to enjoy more and get more out of computers. And hopefully we would have systems that can do inference, modeling, and optimization in one go. Thank you.
Thanks, Antti. So I think Antti was hopefully able to convince everyone here that he's not being around for several occasions because he happens to be convenient nearby, but because he's actually doing world-class job in the domain, which is very, I think, closely associated with data-driven design. We have time for some questions, comments, responses.
You can also find me over the break with a demo.
Yeah, do you care to say a few words about that? It was in the main hall, quite close to the entrance, to the street level.
Yeah, I mean, it's showing these types of ideas applied to web technology. You have a web page, you can collect data in a very easy manner, and what more, you can infer that data and use an optimizer to then push it back to the user, and not only do an ad or recommendation, but restructure the full layout, right? And now we're moving on to use the same structure or infrastructure that we have, which we called optimization as a service, also with the design tools. You can think about Figma or something like that, and we would be able to do the same job there.
I could ask Antti one question regarding, because I think one of the most amazing achievements that your group has had this far was concerning the French standard keyboard redesign, which seems quite amazing thing that Finnish research group ended up doing that kind of work. I'm not going to imply anything about the effectiveness of the French computer scientists, but I'm kind of looking at all the kind of things that you presented. I mean, I think the keyboard design hasn't probably been approved without some sort of like empirical testing, and I presume that that has happened. So I would like to ask that how well did your predictions about the keyboard functionality were matched by the actual results, empirical results that you received?
So this is, of course, one of the benefits of the approach is that you get empirically verifiable predictions. So you produce a design and you can justify to a client that, okay, these are my predictions about usability or aesthetic experience and so on. And of course, when we produce a design, we're mostly interested in evaluating the algorithm and not the ultimate particular design itself. But sometimes we do that and we compare the results to the model predictions. And there's at least one paper that looks at these layouts, and the predictions were, I would say, good for, I don't know, 50% of the objectives that we had, and so for the rest 50. But it only means that it's going to support the designer by throwing away lots of bad designs, right? Because then you can take those as starting points. It has its own capability of doing reasonably good designs, but then you can take up on there and then complete the design.
Okay. If I may still kind of press on the same topic, can you tell which part were the French people most convinced with, so they eventually decided to go with the design that you proposed?
The French people are never happy with anything. And this standard was actually the most heavily debated standard proposition ever in the French history. So we got like 6,000 people, mostly angry, commenting on that. And we worked, it delayed us with 1 year because we actually took them systematically and seriously into account. And we tried to avoid manually changing the interface just because somebody said, but we reformulated the objectives or changed the weights slightly, and with that we got better and better results.
Yeah, that sounds very interesting, and it's been very nice to see this kind of in parallel to the whiskey creation process, that there are some similarities and some differences. Thank you, Antti, so much for coming. Hope we'll see you again.